Hello everyone, welcome to our presentation of the 2019, 2020, and onward iteration of the Compressible Flow Demonstrator, or CFDem. This project was completed by myself, Mario Simon, and David Torgerson under the mentorship of Professor Gloyd Simmons. You can see on this slide our emails are listed in case you have any questions for us. So let us begin with a brief exposition of the previous work on this project. This project is an expansion upon last year's team's work, which consisted of Jacob Yedeka, Carter Myers, and Arthur Flynn. The original CFDem was designed for exit airflow speeds of Mach 2.5 with a regulated inlet pressure of 50 psi absolute and an exit pressure of 3 psi absolute. The previous CFDem was temporarily installed in the welding lab and utilized a borrowed tank. The system accomplished its goal of producing supersonic flow, but did not produce Mach 2.5 due to losses upstream. It suffered from a lack of expansive and accurate data in conjunction with short run times due to a large throat area. As a result of the shortcomings of last year's model, goals and parameters were put into action for the 2020 iteration. The 2019-2020 system aims to exist as a permanent fixture in the Fluid Dynamics Lab of the Natural Resource Research Center, while producing fluid, supersonic flow, shock waves, expansion waves, incipient flow separation, and unavoidable flow separation. Furthermore, the CFDem must be designed to allow for future additions of either a Schlierian photography or shadowgraph system to provide for visualizations of the aforementioned compressible flow phenomena. In order to accomplish this, a permanent air supply of a reasonable pressure and volume is required, along with a new nozzle. The system must be expanded to accommodate a longer runtime and greater data tracking capabilities. After identifying the goals of the system and the characteristics of the NRRC, a setup consisting of new building airlines, a booster pump, and a blowdown tank or run tank were selected. A design proposal was developed after further narrowing of the possibilities and requirements of the system. Runtime minimums were established to ensure that all parts of the blowdown process are observable and significantly logged by the transducers. To give a wide array of price options, 3 tank sizes were proposed. The largest and most easily expandable setup was chosen, and consists of a 120-gallon vertical tank supplied by a booster pump capable of pressurizing the system to 200 psi. Given the 120-gallon run tank pressurized to 200 psi by the booster pump, very substantial run times are obtainable. The greatest run times while producing continuous supersonic flow are achieved when regulated inlet pressure is set to 43.5 psia. At this pressure, we expect to see a remarkable 42.7 seconds of supersonic flow at Mach 2 while maintaining regulated pressure. This will give us excellent potential for Schlierian photographs or shadowgraphs. Incipient flow separation will begin at about 44.6 seconds, and the flow will degrade further to unavoidable flow separation at about 65.4 seconds. These values were found using the blowdown code and analyzing the system parameters and new nozzle design.
The nozzle is made of 5 main pieces: an aluminum upper and lower nozzle body and adapter plate, and Lexan side plates. The adapter plates bolt to a matching plate on the flow straightener. The side bolts are grade 5 1032 machine bolts. The nozzle area was determined by performing a parametric study using the blowdown code developed by Gloyd Simmons. The width of 12.7 mm was fixed to the exit width of the flow straightener to induce a smooth flow path. Again, these nozzle dimensions will produce an exit flow of Mach 2 when properly supplied by flow train and compressor system upstream.
Also, industrial standards from Rao's Jet Propulsion Journal were implemented in the nozzle design to cite laminarity in the convergent section of the nozzle. Calculations were made from the equivalent radius of the nozzle throat to specify contour radii. The results of these calculations produced a very gentle and smooth curve, as not to scare the flow.
The original design used a separate part bolted to the top of the nozzle as a transducer manifold. Unfortunately, there were leaks between the manifold and nozzle body requiring a redesign. Our new design incorporates the transducer manifold into the main body of the nozzle. To make room for the additional transducers required by the lab, both the upper and lower nozzle bodies have transducer ports. The side panels are made out of Lexan instead of acrylic, as Lexan is stronger and easier to machine. The side panels fit snugly between the lips on the nozzle body, ensuring an accurate distance between the upper and lower nozzle bodies. Bolts were added between the transducer ports to mitigate potential interference. Gaskets were chosen as the primary method of sealing between the nozzle body and side panels instead of silicone to minimize the potential for creep into the flow channel. Selecting the gasket material was surprisingly difficult as all options were well above our required pressure range. The deciding factors came down to minimum thickness and price. The recess in the nozzle bodies is sized so the gasket will compress to 90% of its original size as per the manufacturer's recommendations. This ensures no creep and an accurate throat width. The choice of 1032 bolts was made due to their availability and use in the previous design. The calculations shown here are the optimum compressed thickness of the gasket, clamping stress provided by the 4 bolts on each, and the maximum pressure the gaskets can be expected to hold given the compressive stress. To initiate a seal, the gaskets require a minimum of 2.1 ksi, which is less than the supplied 2.4 ksi. To prevent overcompression and an accurate channel width, the gaskets are recessed to 1.429 mm into the nozzle body. The maximum pressure the gaskets can be expected to withhold can be found using the M factor provided by the manufacturer and the operating stress. These calculations confirm the bolts chosen are adequate.
In conjunction with the MathCAD calculations regarding the clamping force of the bolts on the gaskets and the ratings of the Lexan sheets, a SolidWorks simulation was used to verify the structural integrity of the nozzle. A simulated pressure of 100 psi was used to prove the design had a significant safety margin, as this value is substantially greater than the design pressure. The simulation showed minimal stresses over the entire nozzle body and associated fixtures, and predicted a deflection in the Lexan of less than 0.05 millimeters. In these simulations, the gaskets were neglected, as accurate simulation of the proprietary Garlock material is not supported by SolidWorks.
Shown here is a short simulation of the machining process. Stock to be removed is shown as transparent red, and the final part is shown as solid gray. The first operation is the intake side of the nozzle. First, we use a 1/2-inch spot drill to pre-drill the holes. Next, we drilled the holes with a number 3 drill to depth to bolt to the adapter plate. Finally, we clean up the top surface with a 2-inch face mill cutter. The next operation is machining the 3-hole side of the nozzle, including all the bolt holes as well as the transducer holes. Once again, we first spot drill the holes using a 1/2-inch spot drill. Then we drill the through bolt holes with a 1/4-inch drill. Then the transducer holes with an 11/32 drill. Next, we again use our 2-inch face mill cutter to remove the majority of the material from inside the center of the nozzle. Next, we switch to a 1/2-inch end mill to remove the material from inside the gasket pockets, clean up the edges, and cut to length. Next, we switch to a 1/16-inch end mill to remove the remainder of the material from inside the gasket pockets. Finally, we switch back to the spot drill to engrave some reference contours. For the next operation, we machine the 4-hole side of the nozzle. Once again, we pre-drill with our 1/2-inch spot drill, drill to depth with the 11/32, remove most of the material with the 2-inch face mill, and machine the pockets using the 1/2-inch and 1/8-inch end mills. Prior to this operation, I have cut the block in half using a bandsaw along the contour lines I engraved earlier. This operation brings the interior nozzle contour to final dimension with a 1/2-inch end mill. It is then repeated for the other side. Over the next two operations, I drilled the transducer ports. I'm required to drill from both sides because I don't have a small drill long enough to reach from the flow area to the transducers, though the resulting holes on the top side will be plugged using hammered brass pins. The adapter plate is machined from 1-inch stock. First, the excess stock is removed with the 2-inch face mill. Then the holes are pre-drilled and countersunk using a 1/2-inch spot drill. Next, the holes are drilled with a 1/4-inch drill. Holes are also drilled in the slot to allow plunge cutting with the 1/2-inch end mill. The slot is then cleared with a 1/2-inch end mill and finished with the 1/8-inch end mill. The side panels are machined by first drilling the holes with a 1/4-inch drill. The plate is then bolted to a fixture not shown here, allowing a 1/2-inch end mill to trim all the sides to final dimension. The data collection capabilities of the CFDem have been expanded to produce higher data resolution and allow for a greater number of transducers of various types. The TI Launchpad was chosen as it is similar to the existing board and is an industry standard for sensor implementation. The TI Launchpad also requires minimal changes to the MATLAB program written by Bryce Hill. Shown here is a multisim simulation of the circuit representing the additional circuitry necessary to make the board compatible with a 5-volt source. Hand calculations were completed to size the resistors, and multisim was used as a measure of validation. The next steps for this project are to build and calibrate the lab setup. All materials have been specified, designed, and procured. The only thing left to do is complete the nozzle machining process and assemble to run. To complete the data collection updates, a new port will be plumbed into the calibration leg to allow for the addition of a detachable vacuum pump sourced by Scott Kogel. The vacuum pump will be used to calibrate the transducers at pressures below atmospheric, as subatmospheric pressures will be experienced beyond the throat of the nozzle. After recalibrating the transducers, the new calibration data will be applied to the new testing data. This should produce accurate and uniform data from the pressure transducers. Also, the 2019-2020 setup is designed to support the addition of thermocouples and swappable nozzles. This means that the Mach 2 nozzle can be detached and replaced with nozzles configured for exit flows up to Mach 3. The CFDem will be installed in the NRRC 116, the back room of the fluids lab. It will be placed against the east window for viewing during runs. An air line will be run to the corner of the room to hook to the tank and booster system, thus supplying the CFDem with air. Control and sensor wires will be run up the wall and back down to a control and monitoring station on the other side of the window, allowing safe operation with minimal concerns regarding hearing and eye protection. After analyzing data from the previous group, significant deviations between the blowdown code and the actual data were found. We suspect these deviations are due to pressure losses in the flow train downstream of the pressure regulator. Should these deviations persist with our new nozzle, a new flow straightener or flow train redesign may be necessary. The other potential issue we predict will be long fill times for the tank. The booster pump chosen is recommended for smaller tanks, so the fill time may be long when pressurizing the large tank to over 150 psi. While the tank will eventually fill, the time interval between runs may be inconvenient. And here's our bibliography. Special thanks to Gloyd Simmons, Scott Kogel, Bryce Hill, last year's CFDem team, the facilities team, and the mechanical engineering department. Feel free to contact us with questions or to request more information. We have greatly enjoyed the opportunity to work on this project.